Every year, 1 in 4 adults over 65 falls. Falls are the leading cause of injury related deaths in that age group. But the problem isn't just physical. Between 64 and 79% of older adults have what's called maladaptive fall risk appraisal, a mismatch between how afraid they are of falling and their actual physiological balance. Some people are afraid of falling but have good balance, whereas others are have good balance but aren't afraid of falling. Therefore, they don't go to receive help. Our sponsors at UCF College of Nursing developed a framework to classify patients into 4 groups using 2 validated instruments: the Short Falls Efficiency Scale International, which measures fear of falling, and the B-Track Balance Test, which measures postural sway. She then designed an 8-week peer-led exercise intervention program called PEER, built on Otagu's exercise program and ran using a study with 314 older women. The intervention proved effective. Patients showed a statistical significant reduction in their FRA distance, the composite measure of how far they are from an ideal balance of appropriate fear and actual stability. But the study required in person, peer led guides for participants through the exercises and provide encouragement. That's effective, but it's hard to scale.
Our project asks, what if the peer leader lives on your phone? What if a patient can take the FESI questionnaire, get classified on the FRA matrix, receive exercise recommendations calibrated to their profile, perform those exercises with real-time form feedback from an AI that watches their movement and track their own compliance over time, all without a single frame of video or a single word of their conversation ever leaving the device? That's AI peer.
The app uses SMS two-factor authentication through Google Identity Platform. Once authenticated, the patient completes the FESI questionnaire, a validated 16-item instrument that measures concern about falling during daily activities. Their scores plotted against their B-Tracks balance data, which syncs from the clinical REDCap database, and they're classified into one of the 4 FRA groups. This is the same classification framework from the published study, now running in the patient's hand. The app includes 23 exercises from the Otago program across 4 categories: warm-up, strength, balance, and clinical assessment. Before each exercise, the patient watches a demonstration video. The app detects the open palm, confirms the gesture is held for a full second, then counts down 5 seconds before tracking begins. This gives the patient time to get into position without rushing. During the exercise, the app tracks 33 body landmarks in real time. Joint angles, body alignment, and positioning are evaluated against exercise-specific rules on every frame. If the patient's form drifts outside the acceptable range for more than 300 milliseconds, they receive graded feedback: mild, moderate, or severe. At the end of the session, the complete record is persisted locally and synced to the backend. For multi-set exercises, the patient reconfirms with the open palm gesture before each set. No accidental tracking, no confusion about when counting starts.
We use 2 clinical assessments to assess patients and their walking ability. The one shown here is timed up and go. The patient stands from a chair, walks forward, turns, walks back, and sits. The app tracks the full sequence through a state machine: waiting for stand, walking, waiting for final sit. The total time determines their fall risk. Between sessions, the patient can talk to an on-device language model. This is a Qwen 3.5 2 billion parameter model fine-tuned on geriatric health coaching data and quantized to 4-bit, running entirely on the phone. The model supports the peer framework by providing encouragement, answering questions about exercises, and reinforcing the coaching relationship between clinical visits. It is not a diagnostic tool, and it does not replace the clinician. It fills the gap when the patient is at home alone with their exercises and their anxiety about falling. Conversations auto-archive after 24 hours to minimize stored health information on the device. As you can see, the language model can proficiently handle both positive and negative messages related to anxiety and fear, showing it is aligned with the PAIR framework and patient's needs. The patient's exercise history feeds into a compliance tracker. Daily activity, weekly breakdowns, and a monthly heat map give both the patient and their clinician visibility into adherence. In the original PAIR study, the outcome measure was FRA distance, the composite shift in fear and balance over time. Compliance with the exercise program is the key predictor of whether that shift happens. This screen is how you watch it happen. All machine learning inference stays on device. No video frames, no landmark data, and no conversation text ever leave the phone. The vision pipeline runs on a custom vision camera frame processor plugin that we wrote in Swift for iOS and Kotlin for Android. It runs 2 media pipe tasks on every frame: pose landmarker for exercise tracking and hand landmarker for gesture confirm flow. Both tasks share the same native vision framework. Adding hand detection requires 0 new dependencies. When we started building this, no existing React Native media pipe package compiled cleanly with Vision Camera on iOS. Every wrapper we tried hit linker failures or bridging header conflicts, so we wrote the plugin from scratch, validated it in production on real devices, and open sourced it as a standalone package for the React Native community. Pose data flows into a form analyzer that checks joint angles, alignment, and positioning against per exercise rules on every frame. A 300 millisecond temporal smoother filters key points noise so a single glitchy frame doesn't produce false feedback. The rep counter runs a state machine with cooldown timers, minimum movement thresholds, and bilateral averaging for exercises that use both legs. The language model is a 1.2 gigabyte quantized file downloaded once from Google Cloud Storage. After that, inference runs entirely through llama.rn on the device's CPU. HIPAA compliance is structural, not a policy layer. The only data that crosses the network boundary is aggregate exercise statistics, rep counts, durations, form scores. Never raw video, never landmark coordinates, and never conversation text. The architecture itself is the compliance story.
AI Peer takes a clinically validated intervention, the Peer framework developed by our sponsors at UCF College of Nursing, and makes it accessible to any patient with a smartphone. The exercises are guided by real-time pose analysis. The coaching is supported by an on-device language model. The privacy guarantees are architectural, and the clinical outcome FRA distance is tracked through the same validated instruments used in the published research. We are Santiago, Pramod, Arthur, Bailey, and Munish. This is AI Peer, our UCF senior design project for the academic year of 2025 to 2026.